we can like name here maybe a simple start and you can join us.
Yeah, yeah, okay.
Maybe.
Yeah, yeah.
We read
Did you pick up which one? Which one?
yeah,
Which one?
we read the first one.
The entire.
Total.
Oh, okay.
Okay.
Yeah, no, no, but yeah, no, I checked.
So,
Yeah, I'm not sure. So it's the original
sorry.
description.
Hi. Good morning, everyone. So today we are going to talk about parameter estimation. Tali already started to talk with you about it, and he gave you some definitions and review some things, and I will continue. So let's start. Parameter estimation. So we have some observations about the world, and we want to estimate the parameters that gives us these observations. So okay. Question?
Can you open the thing to record?
Right. Thanks. Yeah. Okay. Thanks. So we don't have a direct access to the parameters that we want to estimate. We only have access to the observation. So just recall that the optimal estimator in the Bayesian framework, theta hat, is equal to the arg mean over theta of the conditional risk. Okay? So the conditional risk of theta given our observation. Okay? And in the continuous case, it's equal to arg mean over theta of the integral of the posterior and our risk function, our cost. Okay, so if you give me both of them, I can give you the optimal estimator. Most of the time we have only this term, and now we want to say how the estimator will change if we take different cost functions. Questions? Okay. So Tali started to talk with you about different estimators. So, for example, if we will take the cost function to be, if we want that our estimator will be exactly the true theta, and we don't care that it will be around it. We just want that it will be the same thing exactly. So our cost function will be lambda ij is equal to 1 if I is not equal to j, and 0 in the case that they are equal. Okay? So, in this case, what is our estimator? Right, exactly. So we get it's the map estimator, that this is equal to the arg max of the posterior. Okay?
That's the risk function, right?
This is the risk function. Okay, this is the cost function, and if we have this cost function, or in the continuous case, it's 1 minus delta of theta hat minus theta. This is in the continuous case, and this is in the discrete case. So if we will choose this cost function, we'll get that the optimal estimator in the base DNA framework is the max estimator. Okay? Now, what will happen if we want to pay something if we are not in the right theta, but we don't want that it to be all or everything or nothing? So, for example, we can take the L2 loss, the square loss. So, in this case, we have that the cost function is quadratic. So the cost function is square root the power of lambda theta minus theta hat. And in this case, what is the optimal estimator? It's the expectation of of theta over the posterior. Okay. Now let's suppose that we want to pay something if we are not in the right theta, but the square loss is too much for us. We can take, for example, the norm, or the absolute value of the difference between them, between theta and theta hat. And in this case, what will be our optimal estimator? Right. So this is L2 estimator, and this is L1 estimator, and this is the median of our function. Okay? The median is just the point, maybe I'll write it. So the median is the point that the integral between minus infinity to this point is equal to the integral between this point to infinity of this function. Okay? Here it's the conditional. Sorry, it's the conditional. Okay? So, as I said, we have different estimators
and it depends what we want to achieve. Okay, so we also can say we don't care about we are not Bayesian anymore, and we want to get the best parameters that fit our data. Okay, we have the observations, the data, and we want the best parameters that fit it. So in this case, what we should do, right? The maximum likelihood. So the maximum likelihood, it's R max over theta of the likelihood function, that is the xn, f of xn given theta. And most of the time, it's easier to take the maximum over the log of the likelihood. So we can take the log, so it's the same because log is a monotonic function. And if we have multiple observations, what is the log of the maximum likelihood? Stop. Right. So we can take the argmax of the sum of all the logs of the function. Okay. So again, in this approach, we don't need any prior. Okay, we just take the data and fit it to feed the parameters to the data. Okay. We don't insert here any belief of the distribution, of the original distribution. Okay, now let's just important thing that the likelihood function, okay, is in the likelihood function. So the likelihood function is this function. So in this case, xn are fixed, and we want to find theta. Okay, it's a function of theta, not of xn, because we already have the observation. So when you take the derivative of this and stuff like this, remember that xn is fixed. So let's do a simple example. Now let's assume that f of x given theta is normal with some with theta as the mean and variance 1. Okay, and we now want to find the maximum likelihood estimate. So what we should do, just to put it in this term. So the maximum likelihood estimator is argmax of the sum, right, over all between 1 to n over all the observations xi given theta, and in our case, because it's a Gaussian, this is equal to argmax over theta of minus half sum between 1 to n xi minus theta to the square minus half of log 2 pi. Okay? And because this is constant, we just take the arg mean of the sum of xi minus theta to the square. Okay? And if you will take the derivative of this, you will get that the maximum likelihood estimator is sum over all the xi, and we need to normalize it with 1 over n. Okay? Now, is it clear? Good. So now let's assume that we are Bayesian again, and someone give us prior. So let's assume that we have some prior over theta that is Gaussian with some mean and variance 1. And we want to ask what all the estimators in this case, okay, or what is L1, what is L2 estimator, and what is the math estimator. So what we need to do to find all of them? What we need to do in order to find all the Bayesian estimators, right? We need to calculate the posterior, and then we can find all of them. Okay? So let's do it. So the posterior f of theta given xn is equal to f of, right? F is proportional to f of xn given theta, f of theta, and this is equal, because both of them are Gaussian, this is equal to 1 over square root 2 to the 2 pi to the power of n exponent of minus half sum over I between 1 to n xi minus theta to the square times 1 over square root of 2 pi, the exponent of minus theta minus mu 0 to the square divided by 2. Okay? And we can open it, and
Why is there an exponent inside there?
what?
Why is there an exponent inside the other?
No, this is the first, this is this term, and this is the prior. So, Okay, and this is proportional to the exponent of minus half sum over I between 1 to n xi minus theta to the square plus theta minus mu 0 to the square. Okay, and this is proportional to the exponent of minus half. I'm just I'm just open the square here. So this is equal to exponent of minus half n plus 1 theta to the square minus 2 theta sum over xi plus mu 0 plus mu plus sum over xi to the square plus mu 0 to the square. And this is equal, we have I have here theta and I have here theta to the square, and also a term that it doesn't depend on theta, so this is equal to the exponent of minus theta minus 1 over n plus 1 sum over xi plus mu I to the square divided by 2 times 1 over n plus 1. Okay, and what is this? What is this term? What is this distribution? What? It's a Gaussian distribution, right? It's a Gaussian distribution with yeah. It's a Gaussian distribution with mean of this mean, right? And variance of 1 over n plus 1.
What is the mean?
What?
What is the mean?
This mean.
N plus 1, you say?
No, sum over xi plus mu 1 over n plus 1. Okay, because remember, it's a function of theta. Okay? The variable here is theta.
The variance, it shouldn't be 4?
Okay? Questions?
But it's not normalized.
Yeah, right. It's proportional. You can normalize it. You can try and see that it will normalize. It's a distribution. It must be normalized. Okay, so we get that. So we get that the posterior distribution is a Gaussian distribution with some parameters that depend on the observation. Okay, with some parameters that depend on the observation, and also on the number of samples of n. So if, as we saw, the posterior is random variable, a Gaussian random variable with this mean and this variance, okay, what can we say about the estimators? What can we say about the map estimators? What is a map estimator? Right. So if we have a Gaussian distribution, where it get the maximum? Right. So the map estimator is 1 over n plus 1 sum over xi plus mu 0. Okay. What is the L1? What is the median of Gaussian distribution? The same, right? The same, and also L2. So okay, so we get that in this case, in this spatial case, all the estimators, all the Bayesian estimators that we saw are in the same place. It will give us the same answer. Okay?
Because it's maximum and the minimum and the median are the same, right?
Yeah, exactly. In the general case, it's not true. In the general case, we will get we may get different estimators. That L1, L2, and the map estimators are different. We'll see some exceptions. Okay? It's because it's Gaussian, and Gaussian, most of the things are simple in the Gaussian case. This is the reason that one of the reasons that we are looking on the Gaussian case a lot of times. Okay, so as you can see, so in this case we have the prior. Okay, so the prior is the normal distribution with mu0 mean. So you can see that the prior gives us some, you can think of it as a dummy observation about our mean. So we offset it if we want. You can think of it. We have some examples, and we say that they are Gaussian, and we have some belief that it came from another Gaussian. And we say that, okay, so that our belief that it came from another Gaussian is just like another observation. So this is the dummy observation of our prior, and we need to normalize it with n plus 1 example. It's more intuition, right? This is the estimators, and the intuition of it is that before we have some prior, okay? If we don't have prior, so we saw that the maximum likelihood is sum over xi divided by n, right? We saw it before. And now I'm telling you that I have prior that is Gaussian, and you can see that the map on all the estimators, this is their value. Okay, so it's like, so as I said, the likelihood, the maximum likelihood is this, is normal distribution. It's 1 over n sum over xi, right? This is the maximum likelihood. And the prior just give us one more example, that one more observation to update our belief or our estimator.
You're just saying that as we update different observations, we update our model for different observations, the prior is another?
Yeah, in this case, it's only in this case. In this case, we are looking at it as just one more observation.
So the mu0 is the prior, and the +1 is for the prior, also for the prior, right?
Yeah, exactly. Exactly.
Is there a way to include how certain I am of my prior? How much weight?
The variance, so you have the variance. The variance is, you can take the variance of how much.
The variance is the percent?
Yes. The variance of the posterior, and it goes to 0. As you get more examples, I'm more sure that this is the true value.
My uncertainty of how certain I am of my prior, how much weight do I want to give my prior knowledge in respect to the new?
So you can think of, of course, that you can give in the general case, in this case it's not you cannot do it, but in general case, of course, you can say let's see that I am very confident in my prior, so let's give him some more weight, but it will not be a maxima posterior. Okay.
So the mu0 is not inside the sum?
No. No. It's sum over xi plus mu0. Okay. Just.
Sorry, it was inside the sum when it was squared. So if it's inside the sum, then you take the prior n times.
What?
The mu0 was inside the sum when it was squared. When the expression was squared.
Yeah.
So this means that the mu0 is inside.
No,
the sum.
it wasn't. It wasn't inside the sum. Inside this sum, no. It's.
Sorry.
No. This is here. It's the sum. Sorry.
Yeah.
Here is the sum. It's only on the x side. Okay, and so as you can see here. So as you can see, when we get more and more observations, our prior will be less and less important. Okay, is the effect of only one example? If we have a lot of examples, is not very big.
So you just mentioned that in this case, prior is another observation, right?
Yeah, we can look on it as another observation.
But is there any other case that prior have a very important effect for the MSE?
I didn't understand.
Is there any other case that the prior knowledge that strongly affect the MSE?
What?
If you have not many observations.
So, okay. So in this case, it's very simple, because we know we have the same distribution, Gaussian distribution of the prior, and the likelihood will stay Gaussian distribution. Okay, and we just update our parameters. It's a case that it's called also a conjugated priors. Okay, so we have prior, that in this case Gaussian, and we have the posterior that is Gaussian, and we have the likelihood, sorry, that is Gaussian, and also the posterior is Gaussian. But maybe I will show one more example that of conjugate priors, but in the general case it's not true. Okay? But here we just need to update our parameters according to the observations and the prior. More questions? Great. So as I said, when we get more observations, our variance will shrink, and we will say our confidence in our estimator will become bigger. Now let's see. Okay, so what is the expected value of these estimators? So the expected value of the maximum likelihood is just the expected sum over the expected value of the xi, right? 1 over n. And this is equal to theta, and the expected value of the map estimator is equal to the expected value of 1 over n plus 1 sum over xi plus mu 0, and this is equal to n divided by n plus 1 theta plus mu 0 divided by n plus 1. So in this case, so the map estimator is biased. Okay, we'll talk a bit about biased estimators, but Tali already mentioned it, right? Bias and consistency. So the expectation of the maximum likelihood is estimator is equal to theta, but the expectation of the map estimator is not equal to theta. Okay. So so as I said, as opposite to the Bayesian estimators, the maximum posterior estimators can also found without finding the real posterior. So the maximum posterior, right, is equal to argmax of the posterior. Okay, and we know that this is equal to argmax of the likelihood times the prior. And if we take log of it, we get that it's equal to the sum of the log of the posterior plus the log of the prior. Okay? And this is what? Oh yeah, it's this. What? No, this is yeah, theta, right? It's not. And this is, of course, this is equal to the sum, right? Because they are independent. So we have here two terms. That one of them is dependent on n, right? Is changing as we get more observations, and one of them is the prior that it's fixed. And when n become more and more become bigger, and we get more and more observations, it converges to the map estimators converge to the maximum likelihood estimator. Okay? So if we don't know, or if we can't estimate the maximum posterior estimator, if we have a lot of observations, a good approximation is just to calculate the maximum likelihood. Question? Okay. Also, if we have a uniform prior over theta, the maximum posterior and the maximum likelihood are equal. Time? Yeah, we'll do it after the break. Okay, so break, and if you have any questions, come. Alma? איפה עשית נגזרת? כן, תגזרי את זה לפי תטא. תגזרי את זה. זה יותר חשוב.
זה 2 על פחות תטא.
אפשר לעשות את זה. את גוזרת את זה לפי תטא, אז יש לך פה בעצם, כן, יש לך פה תחשבי שזה שיש לך פה הרי סם over xi, נכון? מינוס 1, סליחה, מינוס נגזרת, נכון, אבל תחשבי, את גוזרת לפי תטא, זאת אומרת שהנגזרת הפנימית, יש לך פה הנגזרת הפנימית של כל זה, כן, נכון? זה מינוס 1, נכון? אז יש לך כאן פשוט פקטור של מינוס 1, ואז יש לך 2, נכון? של התטא, ואז כל הסכום הזה. x, כן, x פחות תטא. סכום, בדיוק, סכום של n, סכום על xi של n, ואת מעבירה את זה, זה שווה ל-0, את מעבירה את זה לצד השני, זה צריך להיות, את מעבירה את זה לצד השני, ואת מקבלת את זה. זה החצי הזה והחצי הזה מתבטלים. את מקבלת סכום על xi. לא, אבל זה קצת מבלבל, אבל בעיקרון מה שקורה, זה תמיד ככה. מה זה תטא כובע, כן? מה זה תטא? אפשר להגדיר את זה בתור תטא, אבל תטא כובע זה לא משנה. מה שאנחנו רוצים זה למצוא את הפרמטר תטא שמקיים את זה. אוקיי? אז ברגע שאנחנו גוזרים, ברגע שאנחנו מוצאים, אז זה בעצם, מה שאנחנו בעצם עושים זה למצוא את תטא כובע. בסדר? כן. נכון. מה?
אתה משתמש בניימן פירסון, ניימן פירסון מדבר על השפעה במבחן שהוא threshold ומבחן שהוא לא threshold, אז כאילו זה מוזר לעשות. כן, כי כאן זה כאילו אותו מבחן, זה אותו מבחן של מקסימום likelihood ratio, אבל התטאות זה לא כאילו מבחן שונה, ואז אני לא בטוחה שאפשר להשתמש בניימן פירסון בשביל להוכיח את ה-well defined, מה גם שפה זה מראה שזה לא well defined.
לא, זה... שנייה. זה לא... זה מה שנייה. זה well defined, זה כן, זה well defined, אפשר הוכחנו את זה בזה. זה על סמך, נכון, נכון.
אבל שונים, ותטא זה לא שונים,
נכון.
אז איך אתה יכול לשתות את המשפט הזה שמשווה בין שני מבחנים שונים, כשכאן יש לך אותו מבחן?
אז זה בדיוק מה שאנחנו רוצים שכאילו זה בדיוק העניין של לחשוב על זה כאילו זה בדיוק זה שכן, זה נכון מה שאת אומרת, כאילו זה באמת לא, באמת ה-ROC curve לא מוגדר, כאילו זה שיש לך מבחנים שונים, כן, לא אומר שיש להם נקודות שונות על ה-ROC curve בעצם. זה
אז זה סותר את זה. יש לי פה תטאות שונות, נגיד זאתי וזאתי, שעבורם אלפא שווה ל-0 כי כולם אני מתייגת נכון כאומגה 0, אבל הבטאות שונות. אז יש לי תטאות שוות עבור תטא, כאילו אלפא שווה עבור תטא 1 ו-2, אבל בטא שונה, שזה מה שאני מקבלת כאן. זה סותר את מה שאמרנו בכיתה שה-ROC הוא well-defined.
תחשבו על זה קצת, זה לא, אנחנו רוצים לא, בעיקרון זה באמת הפרדוקס כאילו שזה, באמת מה קורה שיש perfect separation, זה באמת זה בדיוק זה, שה-ROC כאילו ה-ROC שלך הוא בעצם, הוא לא פונקציה. נכון.
אבל הוכחנו את זה כתכונה של ה-ROC, אז איך יכול להיות...
לא, שנייה. רגע, שנייה. מה הוכחנו פה, כן? עבור תטות שונות, כן? יש זה. העניין הוא פה, זה לא התטות השונות. אין לך פה, כשאת עושה את זה, אין לך תטות שונות בעצם.
זה בדיוק תטות שונות, זה בדיוק לקבוע סף שונה, שמפריד בין W0 ו-W1.
לא, אבל שיש לך perfect separation, זה כאילו בעצם מה שיש לך זה בעצם תטא 1.
למה?
בעצם...
לא, פה יש לי perfect separation של תטא 1, אבל עדיין זה שתי distribution שהם ב-perfect separation. תטא זה מספר, הוא לא יכול להיות
נכון. מה זה?
תטא זה מספר, אם יש לי 1 ו-5, זה מספרים שונים, אז יכול להיות פה 1 ו-5.
כן, אבל... נכון, לא, אבל הרי...
זה גם לא קשור, גם אם הם אותו דבר. לא, זה דבר זה לא. לא, אבל התטא היא כל הדבר הזה. זאת אומרת, אני יכולה לשים את הסף בכל נקודה דיסטריביושן ובכל נקודה דיסטריביושן.
כן, אבל תחשבי על זה, שנייה רגע. אבל שיש לך... יש לך את ה-likelihood, את המקסימום likelihood. אוקיי? ושאת מסתכלת על הרשיו של ה-likely. אוקיי? מה קורה כאשר יש בעצם perfect separation? יש לך בעצם שתי הפונקציות, כן? זה יכול להיות רק, את אף פעם לא תהיי מוגדרת בעצם, כאילו זה תמיד יכול להיות רק או 0 או 1, לא יכול להיות לך, תחשבי שיש לך את f של x given theta 1 ו-f של x given theta 2, כן? אז אם בעצם, אם זה 0, אוקיי? נכון? אם את לא מוגדרת כאילו פה, אז בעצם, אז את יכולה להגדיר את זה בתור 0, את יכולה להגדיר את זה בתור 1, אוקיי? את יכולה להגדיר בעצם את הרשיו הזה, כן? את צריכה בעצם להסתכל שהרשיו הזה בעצם, העניין הוא שהוא לא מוגדר לך כאן. כי אז בעצם, כי ברגע שאת מסתכלת על יחס הנראות, כן? את בעצם לא יכולה להגדיר, כאילו, מתי שאין לך separation כזה, את לא יכולה להגדיר בעצם תטא כזה. אוקיי? את לא יכולה להגדיר תטא. כי הדבר הזה הוא לא... הוא לא מוגדר כאילו זה, כי הוא בעצם 0 או 1. כי הוא בעצם... בדיוק, כי הוא בעצם או 0 או 1.
להסתכל כאילו על משהו כזה. זה לעשות משהו... זה כאילו הסף.
לא, אבל את לא...
כאילו זה גם כמעט שקול.
זה כמעט זה, אבל את לא יכולה לעשות את זה.
לא, כי אז אחד...
לא, כי אז בעצם, כי עוד פעם, יש לך כאן, את מגיעה לאותו דבר, שיש לך כאן כאילו 0 ו-1, ואז כל הביטוי בעצם הוא מנוון.
אתה אומר שכל פעם שאני נמצאת באזורים של ה-0, אז התטא לא מוגדרת? הסף כאילו לא מוגדר?
בפועל כן. בסופו של דבר, מה שקובע, במקרה הזה, מה שקובע את ה-arrow seeker זה באמת כאילו שעוד ב-0 עוד ב-1. כאילו, זה מה שקובע, אבל את לא עוברת דרך, בעצם את לא עוברת דרך המון תטא בשביל זה.
אבל כאן, גם אם אני נמצאת פה זה מוגדר, נכון? או שאתה אומר ששום דבר לא מוגדר, כי בעצם בכל מקום, אם אני, כאילו בכל מקום לפחות אחת מהדיספוזישן זה מוגדר.
בסופו של דבר כן, זאת בדיוק הבעיה כאילו שאתה... הרבה פעמים נגיד שאנחנו רוצים לחשב, לא יודע, המון דברים
ש... למה לעבוד ככה? כאילו פה זה בסדר.
לא, זה לא בסדר, כי את בכל מקרה, כי את לא מקבלת...
אז איך?
כי אין לך... מה?
זאת אומרת שתטא לא מוגדר, זה לא שאתה מייצר arrow seeker
אז זה בדיוק העניין, שאת רוצה...
אתה רוצה לדבר זה לא מוגדר?
אז זה בדיוק העניין, או שאתה אומר שהוא לא מוגדר, אנחנו פשוט רוצים שתחשבו על זה פשוט, אבל בעיקרון, כן, או שאתה אומר שהדבר הזה לא, אני לא יכול, ברגע שיש לי perfect separation, אז אני מקבל בעצם, אין לי arrow seeker, כן? יש לי בעצם, או אני בנקודה הזאת או בנקודה הזאת. או שאתה מגדיר אותו בצורה הזאת, כאילו שאתה מגדיר אותו באמת בצורה הזאת, שזה בעצם נקודה, כאילו, במרחב הזה. וזה לא קרב.
אבל קרב לא מחייב שזה פונקציה.
נכון. זה לא פונקציה, סליחה, זה קורבה. נכון, זה לא פונקציה, נכון. זה קרב בעצם עם קרב מנוון.
אבל זה נכון פונקציה, לא?
הדבר...
אני לא מבינה איך אותך השתמשת בזה שזה חייב להיות מוגדר. כאילו איפה... אם הבעיה הזאת קיימת, אז איפה שבהוכחה על כך צריך להניח על זה משהו שמבטל את זה, כאילו שזה יהיה well defined.
כי מאיפה התטות האלה? לא, זה מלוג יחס... מיחס הנראות.
בעולם שלי, להגדיר את האלפא שלו ואת ה... בסדר, אני יכולה לבחור פשוט שני מספרים, גם אם היחס הזה הוא לא מוגדר בהם.
את יכולה לבחור שני מספרים את יכולה לבחור שני מספרים, עוד פעם?
אני יכולה לבחור שני ערכים בעולם שלי ושקצת, אני יכולה לעשות גם אם זה לא מוגדר.
איך? לא, כי הרי יש לך...
How much is your number?
כאילו, זה שיהיה גם אחד, אבל אני יכולה לעשות את זה.
אוקיי, אז זה יהיה 0 ו-1.
אז איפה בהוכחה השתמשת בהנחה, כאילו...
שמה?
יש תחום שזאת הייתה לא מוגדרת. כן, כאילו, איפה זה...
שיש
This
תחום
year is the first year.
כן. כי אני לוקח את אלפא להיות פונקציה של תטא. ותטא אני מגדיר... בסדר, אפשר לעשות את זה, להגיד נכון, אני אומר שתטא לא מוגדרת בכל מקום. עכשיו, אם אתה עובר דרך העניין של התטות, כן, אם אתה מגדיר את אלפא בעזרת תטות, ומה זה תטות? תטות זה יחס הנראות, אז אתה לא יכול לעשות את זה. אם את סתם מגדירה... זה איזשהו threshold על יחס הנראות.
כן, אבל אחד פרוטות שבא לי בין 0 לאינסוף.
את יכולה, אבל את צריכה רק שזה יהיה מוגדר. שאת תוכלי לעשות את זה. את יכולה, אבל זה בדיוק העניין. זה פונקציה של... את מה?
השאלה היא כמה שימושי הוא יהיה לי, אבל אני לא מבינה למה...
לא, אז את לא... מה זאת אומרת? את לא יכולה לבחור, כאילו... את יכולה לבחור, אבל הוא לא... אבל ברגע שאת מגדירה את... ברגע כמו שאנחנו עשינו, שאת מסתכלת על אלפא שבעצם את קושרת אותו ליחס הנראות, כן? ברגע שאת קושרת את... צריכי בניימן... לא, אבל בהוכחה של... נכון, אבל בהוכחה של... בהוכחה שטלי הראה לכם בכיתה של ניימן פירסון, שמה...
כן, כי ניימן פירסון משווה בשני מבחנים שונים, לא באותו מבחן של אייקליוד ריישו עם שני מבחנים שונים.
ניימן פירסון משתמש בשני...
במבחן אחד שהוא אייקליוד ריישו, לבין כל מבחן אחר שהוא לא אייקליוד ריישו.
לא, אבל הוא...
וכשאתה שם שני ספים שונים זה לא שני מבחנים שונים, זה אותו מבחן עם סף שונה.
לא, אבל את יכולה...
אתה משתמש באם של המבחן, זה של המשפט.
לא, אבל את יכולה להשתמש... כן, אבל את יכולה להשתמש בו בגלל זה בשני הכיוונים, כאילו. את יודעת ש...
זה לא מה שאני אומרת. אני אומרת שהמשפט של הלמה של ניימן פירסון אומרת יש לי את המבחן הזה, שזה ה-likelihood ratio.
נכון.
ויש לי כל מבחן אחר שהוא לא likelihood ratio.
הוא יכול להיות. במקרה הכללי. הוא יכול להיות.
אז מה מייחד את זה? מה מייחד את הדלת טבע?
זה likelihood...
שאתה אומר שזה המבחן הכי
זה likelihood ratio, אבל את יכולה...
זה likelihood ratio, מה המשמעות של המבחן?
לא, אם זה... מה זאת אומרת? אם זה likelihood ratio... שנייה. אם זה likelihood ratio, פה יכול להיות לך likelihood ratio, אבל עם תטא אחר.
Yeah, but like my matter...
מה מייחד את התטא הזאת להיות נזאת?
כי השאלה... אבל אז... רגע, את מסתכלת על... עכשיו, מה שבעצם זה אומר, שאם אלפא של אחד גדול מבטא של האחר, כן? אז את יודעת שהבטא של האחד קטן מהבטא של האחר, אבל זה עובד גם בכיוון ההפוך. בגלל שהבטא של הזה...
אז בעצם כדי להסביר את החומה הזאת, מה שאני אומרת כאן, הוא לא תקף בכלל. כי אתה אומר שהטרשולד לא מוגדר לאורך...
כן. כן, יכול להיות.
אבל מצד שני,
אני רוצה רגע רק לשתות. לפני שאנחנו מתחילים. אפשר, כן. מה... כן. אחרי זה... רגע,
כן, תפת מחר. כן, מה סבבה? השבוע הזה יצא לי קצת כאילו, לא עזבתי באיזה 5, כן, מה סבבה?
מה זה? כן, האמת שזה נכון.
But I like glasses. Like I still don't mind. Like, I feel my face is empty without glasses.
Empty? Empty?
Yeah, I don't know, something missing.
Just you're not used to it, you know.
This is because
How long have
you
you been
can
with
see yourself in the mirror without glasses, so we feel.
Now because
But
of
you
soccer,
raise
I
it.
bought contacts. I haven't
לא,
worn
איך היה?
contacts since
יש את
the
נו,
army.
איך היה ביום חמישי?
And,
כן?
it's weird.
נהנה?
Like, when I was younger, I used to go all the
יש עוד
time
בתי
with
ספר
contacts, but now.
ברחבי ירושלים.
מה?
יש עוד בתי ספר ברחבי ירושלים. יש עוד בתי ספר ברחבי ירושלים.
נלך עליהם?
ביהודה.
בסדר, תן קודם את התרגילים, אתה מציע לי פה הצעות מגונות. אבל היה ממש כיף. היו כאילו חמודות וכיפיות, מלא סקרנות, הרגשתי ממש בנוח. לא יודעת, הייתי כאילו אולי סוג סטריאוטיפי, שהיה לי בראש שזה יהיה כזה ילדות טובות ירושלים,
יכול להיות ילדות טובות
ילדות
ירושלים.
קונפורמיסטיות כאלה.
יכול להיות שלכם כאלה.
אבל לא, הם דיברו כזה חופשי, היו חשופות כזה, כאילו חשופות בקטע טוב, לא בקטע רע, בקטע כזה, לא יודעת.
כאלה אנחנו הדתיים, אנשים רגילים.
מה, זה לא שלא פגשתי, נגיד שבאתי לצבא והייתה איתי מישהי שהיא מקשת.
כן.
בסדר.
קשת.
בסדר, אני לא יודעת, ואני אומרת לך מה האקזמפל שלי, כאילו אני לא אומרת שאני צריכה לעדכן את
גם כשאני מגיע לקשת אני מרגיש שאני בפלנטה אחרת.
מה?
כן.
היא הרגישה, כאילו הרגשתי שיש פער עצום בינינו, היא הייתה מאוד מובנת ממני ואני הייתי נורא מבקרת. כאילו זה ממש לא עבד.
כשאני מגיע לקשת אני מרגיש כאילו בפלנטה אחרת.
כאילו לא כל שהחילונית והיא הייתה השנייה מהיישוב שהתגייסה לצבא, ואחותה הייתה
קשת זה פלנטה אחרת.
כאילו להיות באותו חדר, יותר אינטנסיבי לפגוש אותם בחדר, רק בלימודים.
No, Tali will come, hopefully. Okay. So. Okay. So in the previous hour we saw that the maximum we can write maximum posterior as the maximum likelihood plus the prior. Now, okay, so now let's do one more example. And now f of x given theta is equal to theta e minus theta x. Okay, the exponential. And the prior is equal to e minus theta. And as before, we want to find the maximum posterior and maximum likelihood. So, what we need to do? So we know that this is the posterior, right? This is the maximum posterior. So first we need to find what is the sum over n of log f of xi given theta. Okay, and if we put it here, we know that this is sum over n log of theta minus theta x I. Okay, and this is equal to n log theta minus theta sum over xi. Okay, plus some constant. And log of the prior. What is the log of the prior?
Sorry, why plus
Never mind, you can ignore it. No. What is the log of the prior? Right, minus theta. Okay, and if we differentiate it with respect of theta and compare it to 0, we will get that the derivative of f of theta given xn with respect of theta is equal to the derivative of log of xn given theta plus the derivative of log of the prior. And this is equal to n divided by theta minus sum over xi plus 1. And we want that this will be equal to 0, and we will get that the map estimator is n divided by sum of xi plus 1, and the maximum likelihood estimator is n divided by sum over xi. Questions? Okay. So this is just, it's the inverse of the average, right? The average, the mean. Now, Tali already talked with you about it, but let's just do a small, quick reminder.
Is there a better marker?
Let's see. Red. Let's try. Better? So, consistency. What is consistency? Okay, so if we get more and more data, right? We want that the estimator will getting closer and closer to the real theta. Right? Regardless of the value of theta, we want that our estimator will become more and more closer to the real parameter that we want to estimate. So basically, this is consistency, and we formalize it as for some xn observations, we want that the probability of our estimator to be equal to theta. What will happen to this term when n goes to infinity? Right. This will go to 1. Okay? So in probability, we want that as we will get more and more observations, our estimator will become closer to the real theta. Okay, so this is a consistency.
Would the stronger claim in saying that the variance will go like 1 over square root of n? Or
It's what?
is it any different than saying that the variance will go like 1 over n?
Yes, because here I didn't talk about the distribution.
Or it would be like a series of delta function and then it's not true, but the variance.
What?
No,
Okay, later you can. The next thing is biased or unbiased estimators. So we want, of course, that estimator in the expectation, in the expected value, will be equal to the real parameter. So unbiased estimator is estimator that the expected value of it is equal to theta. Okay? And here the expected value is over xn, okay, of all the samples that we can get. So this is a consistency and unbiasedness. As we saw the maximum likelihood. Tali showed you, I think, that the maximum likelihood is consistent, right? He didn't show you? Okay. Okay, so I will not show it, but we will see some other property of.
So you said now that the maximum likelihood is always consistent?
Yes. So the maximum likelihood. Let's see some properties of the maximum likelihood. Okay. So the maximum likelihood. First of all, it can be biased. Okay. Let's see some examples. So first of all, can be biased. Okay, so for example, we have our observation is the f of x is given some u and sigma to the square is normal distribution. Okay, and so we have some observations that come from normal distribution, and we have two unknown parameters: the mean and the variance of the Gaussian. Okay.
Normal with the three.
It's normal. X is normal. It's mean and some variance. Okay. And now we want to find the maximum likelihood of this observation. So in this case, theta is both the mean and the variance. It's a function of two variables. So now let's find the maximum likelihood. So what is the maximum likelihood? We need to find the likelihood first, or the log likelihood. So the log likelihood of f of x given theta is equal to the log of 1 over square root 2 pi sigma to the square n, right? Because we have n observations, n exponent of minus sum of over all the xi minus mu to the square divided by 2 sigma to the square. Okay? And this is equal to minus of 1 divided by 2 sigma to the square sum over xi minus mu to the square minus n divided by 2 log of 2 pi sigma to the square. And if we take the derivative of this with respect of theta, we will get that mu hat, the maximum likelihood estimator of mu, is equal to 1 over n sum of xi. Okay, so of course it makes sense if the mean of the distribution, the mean of the likelihood is just the average of all of our examples. Okay, it's clear. Now we want to find sigma, right? Sigma, the variance of the Gaussian. So so instead of take the derivative with respect to mu, we will take the derivative of the variance of sigma to the square. So d log f of xn given theta divided by d of the variance is equal to 1 over 2 sigma to the square sum over I xi minus u to the square minus n divided by 2 sigma to the square. And this is, we want that it will be equal to 0. And of course, so we can get that this is sigma to the square of the maximum likelihood estimator is equal to 1 over n sum over xi minus mu mu hat to the square. Okay, and again, it makes sense because we will take the sum of the variance of our observations. Okay. Is this estimator is biased? How can we find if it's biased? Exactly. So, okay. So we will take the expectation of it. So first, let's find. Let's find the expectation of sigma square, the maximum likelihood, given theta, right? So this, we know that this is equal to the expectation of 1 over n sum over xi minus mu, the estimator of mu to the square given sigma, and we can open it and take 1 over n outside, and take the sum outside, and we get that we have this is equal to the 1 over n sum of the expectations of xi minus, we will add here some dummy variable mu. We will add mu and subtract it. Okay, this is to the square, and now we can separate it. So this is equal to 1 over n sum of the expectations of xi minus mu to the square plus 2 xi minus mu times mu minus the estimator of mu to the square, plus mu minus the estimator of mu to the square. Okay, and this is given theta. Okay, and we can open it. This is, what is this? Right, and this we can take the expectation inside it, and this also the variance. So at the end we will get that this is equal to sigma to the square minus 2 the expectation of 1 over n sum over mu minus xi mu minus the estimator of mu given theta plus sigma to the square divided by n. And now, what is this?
Why is it exponent?
Why this? Because we have this. It's, you can open. Oh, okay, so maybe I do it maybe slower. It's because you have so this is okay. So this is the variance, right? This is we just take into the variance, and this is just a second. No, just a second. U minus mu plus u to the square. So the expectation of this is oh no, sorry. It should be no, sorry. This is it's mu. It's the expected value. It's the expected value because we can take it's the sorry. So this, right? We can write it as the expectation of mu to the square. What? No, the sum is the sum is over. We can write it. So it's the sum over the expectation of mu to the square minus 2 mu to the square mu, the estimator of mu, not the estimator of mu, right, plus u to the square, the estimator of mu to the square. Okay, and we have here, so we have here maybe it's more it's a bit okay, sorry, divided by n. Yeah.
No, the n is cancelled.
You can take yeah, it's divided by n. You're right. So we know that we have here 1 over n, the expectation of mu to the square minus 2 mu the estimate of mu, right, plus maximum likelihood of mu to the square, right? This is, we know that, okay? And now this is, okay, so this is here we have the expected value, we have the expected value of mu. Mu is the expected value of x, right? So, and here it's constant. So we have here basically the expected value minus x, if you want. The expected value minus mu. We have here the expected value minus we have here this. Okay, so and this is exactly plus minus this term. So it's exactly the variance of x.
The expected value of the new estimator is the estimator test?
What?
Like, why did you take the estimator out of the expected value?
The expected value of the estimator is a constant regarding the.
But now we're talking about the expected value of the other estimate.
Right. So the expected value of mu, of the estimator of mu, is constant with regard to the expected value of sigma to the square.
What if x is mu?
It's, yeah.
So how is it? I don't understand why the first term is the effective value of x to the power.
I will upload it to the Moodle, okay? I don't just, we have some more things. I will upload it. Okay, I will upload the detailed explanation. Okay. Okay, so yeah, the point is that at the end we will get the expected value of sigma to the square of maximum likelihood sigma to the square given theta is equal to sigma to the square n minus 1 divided by n sigma to the square. Okay? This is the point. And the point is that this estimator is biased. Okay? But if we will take n to infinity, if n goes to infinity, then sigma to the square, sigma hat to the square is equal to sigma to the square. Okay.
And where's the second term there?
So we will get that this at the end we will get that we have this term, and sigma to the square divided by n. This estimator is biased, but it's also consistent. Okay.
But wait, if you take n to infinity,
yeah.
then what?
Then we have here that sigma, the estimator of sigma to the square is equal to the variance. Okay. And we can correct this term if we want unbiased estimator. We can define sigma to the square of this unbiased estimator is 1 over n minus 1 of the sum of xi minus mu ml. Okay, this is unbiased.
Can you repeat again? Where did the second term go?
Here?
No, the other one.
This one? Where is it go? What do you mean? It's the expectation of is the expectation of mu minus mu, the estimator of mu.
And it's 0?
And it's, yeah.
Because the maximum
No,
likelihood
it's
mu
not
is
zero.
consistent, is not biased.
Is not biased. Exactly, because it's not biased.
No, if it's 0, then that's plus.
What?
No, I mean, if the middle term is 0, then this side should be plus, right?
What?
This?
This?
It's plus or minus 1.
No, but it's not 0 because it's squared and it gives you minus
No,
times
just
the last term.
it's no, sorry. You know what? I will upload it because okay. So no, it's not 0. You're right. It's 2. It's 2 times the. Yeah, you're right. It's 2 times the variance of the variance. Sorry.
Again?
It's 2. Okay. I'm sorry. This term. Okay. It's exactly the sigma to the square. 2 times sigma to the square divided by n. Okay? Because this is the expectation this is 2 minus 2 the expectation of mu minus mu ml to the square. Okay? And this is equal to 2 times sigma to the square divided by n.
But if you take the expected value of mu minus the
Yeah.
Are your notes more detailed? Is this the...
I will upload more detailed notes. Yeah. It's the same trick that we did here. Okay. So we can define this. We can define this is. We saw that the maximum likelihood estimator is biased, and now we can define estimator that is unbiased. Okay, this is unbiased estimator of.
of what?
It's unbiased. What do you mean? Of the variance. Of the variance. It's sigma to the square. Okay. So we can see that I will not show you, but you can check that this is unbiased estimator of the variance. Now more biased estimators. You can think of if you have a uniform distribution over some closed interval. So P of x given theta is equal to 1 over theta if x is in some interval between 0 to theta and 0 otherwise. This is an example of biased estimator. So in this case, if we have this distribution, okay, we know that the likelihood in this case, so the likelihood in this case is 1 over theta to the n. That means that we need to take the smallest theta that we can, right? Because if we want the likelihood as big as we can, we need to take the smallest theta the smallest possible theta.
Isn't n the likelihood ratio?
Yeah.
So ratio between what?
It's the likelihood function. It's not a ratio. So it's the likelihood function. We all the time we define the likelihood function as the f of p of xn given theta.
Okay.
When we
That was the ratio. So
no, it's not a ratio. When we want to talk about estimators, okay, we don't have ratio.
right. So it's not supposed to be n.
It's what? It's what? N is the number of examples.
N.
It's
It's not the same as
oh yeah, okay, no, it's the likelihood here. Okay, so yeah, it's the likelihood function here. Okay, sorry. It's the likelihood function here when we want to take the maximum likelihood.
Until now we wrote this function as p x n.
Okay, right, sorry. So this is okay. So p of xn, okay. So p of xn is 1 over theta, and we have here this term, this n term that will bring us to infinity. Now, when theta, so we want the smallest possible value of theta, right? because we want that this will be maximum. So what is the smallest possible of theta in this case? Right, the maximum x. Okay? And the expectation, and so if we will take the maximum x, the expectation of the maximum x is the expectation of, as I said, maximum x, and you can show, I will not show it right now, that the expectation of the maximum is equal to n theta divided by n plus 1. And this is smaller than theta. So in this case also we have a maximum likelihood that is biased. But it's not necessarily bad. There are some cases that we want that our estimator will be biased, or that if we have some trade-off between bias and variance, we want that to pay something and take a biased estimator. Okay. One more property.
Can you repeat why the maximum xi? We're trying to find maximum xi.
Yeah. So the expectation is a general statement or general fact that the expectation of the maximum. I will not prove it here, but if you can come later and we'll show it to you. One more thing is that the maximum likelihood estimator is not always unique. Okay, so we saw that it can be biased, and now we will see that there are some cases that the maximum likelihood estimator is not always unique. Okay, so the example is we have the IID samples that came from the distribution of x given theta is distributed with uniform distribution in the interval theta and theta plus 1. Okay? So that means that p of x n given theta is equal to 1 if all the xi are in this interval and 0 otherwise. So now what we need to choose for our estimator. Of course, what? Of course that we need that theta will be between the maximum xi minus 1 and to the minimum of xi, right? We need if we have the interval. Okay, so here it's the maximum of xi, and here it's the minimum of xi. So here it's the maximum xi minus 1, and here it's the minimum of xi, and and all the theta that we will